Sorry about the technical issues. My name is Jiang from University of Science and Technology of China. Let me start by thanking the organizers for inviting me, especially Roland, for organizing this wonderful meeting. This is my first time to Sweden, and of course, first time here. A beautiful city and beautiful campus. So today I'm going to talk about our recent progress based on a framework that we call the physically inspired embedded atom neural network, and extend it to study the system response to the external fields. So our starting point, actually, as mentioned by the first speaker, is a potential energy surface. That's the essential part or integrates to study many interesting dynamics and the spectroscopy of the chemical systems. And it's in mathematical representation. It's just actually a multi-dimensional function that and this potential energy surface actually has multiple names or terminologies in terms of different areas, right? Some people call it force fields, and some people call it interaction potentials, and so on. But I think the key for constructing the potential energy surface is actually the symmetry constraints that the chemical system has to satisfy. For example, the translational, rotational, permutational invariance, which have been emphasized in literature many times. And I use this slide borrowed from the literature of Pavlo, who is in the audience, and who this literature actually summarized some of the recent machine learning potentials in this field, but not absolutely not all of them, and because this field is very fast developing, and we have many early version of the machine learning potentials before the explosion of this machine learning applications of this area. But we also have some different choices beyond the kernel method or neural network method. And from the this diagram, we can see that there are typically two types of machine learning potentials. One is based on the global descriptors, which means you describe the structure of the system as a whole, and we can use some kind of symmetrized functions to describe the structure. And on the other hand, you can use local descriptors, which means you can describe the atom-centered environment, and then you add the atomic energy together, as just described by Alexander in his talk. And more recently, there's a trend of using message-passing neural network, which is borrowed from the idea of the computer vision machine learning, the graphic neural network. But today I'll focus our own framework and show the connection between the traditional local descriptor and the message passing neural networks. Okay, so my favor of discussing this atomistic of the force fields of atomistic systems actually is going all the way back to the atomic force field. Many of you may know those physically inspired force fields like EANN or Tersov, and which are widely used in early days and even nowadays for simulating materials. And this idea of local approximation, I guess, actually originates from those potentials or force fields. And it actually at very early time, people are thinking of using machine learning. Here is a neural network to optimize the parameters of those empirical force fields and to improve its flexibility. But still, because of its fixed form, that, and as we know, so its lack of the accuracy for describing molecules, which is anisotropic, and also the bound breaking processes. So our starting point is actually also an empirical force field, which is called EANN. The idea is very simple, that you can write the total energy in the sum of atomic energies, and each atomic energy can be expressed as the functional of the local embedded atom density. And this functional is actually unknown, just as DFT. But we can borrow this idea, and you can replace this functional as a neural network. With a neural network, and you can, so this gives you the same form as the well-known Beller-Pranano type of neural network. And of course, because of this formalism, it satisfies the translation, rotation, and permutation invariance, and as well as periodicity as required for the materials. So it's applicable to both molecules and the materials. And what we construct this embedded atom density is from the atom-centered Gaussian type orbitals. That's also a well-known physical concept. Everybody learns quantum chemistry knows that, right? You can use the linear combination of atomic orbitals to get the wave function, and you square it to get the density. So, the implementation is also very easy, and that gives you a linear scaling with respect to the neighbors of an even atomic center. So that's very important, and you can further, use your quantum chemical knowledge, and to use, like, for example, basis contraction. You can construct a contracted Gaussian orbital and apply it to construct this embedded atom density feature. And we just need to reorder the summation, and to prove that now we can use a smaller size of Gaussian orbitals to get the same representability as we have used the primitive Gaussian orbitals before. So all those ideas of quantum chemistry can be applied here. And the key is that we have this high representability by using only the two-body computational cost, because we have only a linear combination here, right? And furthermore, you can also realize maybe the atomic orbital coefficient itself should be environment dependent. So that's what we also know in quantum chemistry, right? When you do the electronic structure calculations, you not only optimize the orbital itself, but also the orbital coefficient. And so we can make an atomic neural network to express this atomic orbital coefficient, then make it update in the self-consistent way, and this orbital coefficient now depend on atomic environment too. So with this feature, you can now distinguish some structures that cannot be distinguished by the regular three-body based local descriptors, for example, our own EANN model. And what's more important is that if you convert this our Cartesian expression of this density feature to the local internal coordinate frame, then each iteration will give you an expansion of two additional coefficients, and each coefficient can be expanded by additional two coefficients. And you do these iterations all the way to the end of t, and that will allow you to incorporate up to this number of interatomic distances. In other words, when you do this kind of message passing way, you automatically include more and more atoms in your descriptors and to achieve the local completeness. We can actually force this term to be greater than the number of interatomic distances of the system. Then you can find the minimum number of message passing descriptors, iterations, and that is 2 for a molecule like methane. And this is actually essentially the same idea of message passing, which is originated from the graphic neural networks and also mentioned in our first speaker's talk. And these are some first generation of message passing neural network. They typically pass the two-body invariant messages. Here, G is a Gaussian function. And we can show that from this diagram, this kind of two-body based invariant message passing cannot describe some structures. For example, if you have these two hydrogen atoms which has a distance beyond the cutoff radius, then these two atoms cannot be correlated no matter how many iterations you are using in this SHINET framework. But since we are using the three-body invariant message passing, then we can correlate those two very distant atoms easily. And we can distinguish those two structures. That will give us better accuracy. So here's the numerical validation of our approach. These are 8 million structures of methane with randomly displaced atoms around hydrogen atoms around the carbon atom. And on the left, I show you this diagram with the linear fitting. In this diagram, we remove all the non-linear features of neural network, only use one linear layer, and then that gives us the pure representability of the descriptor, right? So we can see here, with increasing the iteration, we get better representability of the system. And on the other side, we show that when you add the powerful non-linearity of the neural network, we can get very accurate fitting for the whole system. Our model actually outperforms the two-body-based message passing neural networks. So with this, we can have multiple tests around the molecules and some bulk and surface structures, and also some liquid water, the periodical systems. In all cases, we show that when we get the similar level of accuracy, our efficiency is pretty high. And when you get the similar level of accuracy, our data efficiency is also very high. Okay, so these are already published results, and recently we also recognize that the equivariant feature of the descriptor is very important, and how to adapt our EANN framework to the equivariant version. It's still very simple. Now the current FIREANN model actually only passes the information in this coefficient, which is a scalar value, right? We can simply adapt it by passing not only the coefficient, but also the orbital, which is a vector. So we can update both coefficients and orbitals, and in the form similar to other equivariant message passing neural networks. And the advantage of this equivariant version of FIREANN can be seen in this comparison. You can see here is the cumulin with the variable size of the carbon-carbon double bonds. And when you rotate the hydrogen atoms in the two ends, then you change the potential energy as a function of the dihedral angle, right? And when you increase the length of this cumulin, and you can see many machine learning models failed. For example, the SHINET and the FIREANN give you pretty, completely flat potential with respect to the dihedral angle. And the RIANN model solved part of the problem, but when the length of the cumulin increased to a limit, like there's 9 atoms here, carbon atoms here, then the RIANN model also fixed a field, but the equivariant version can always describe the change of the potential energy surface. Now, let me move to the response of the external field. And this is well known that when you have an external field applied to the system, you sort of add an electric polarization to the system, and the electronic density distribution will change, right? And since our descriptor is based on the electronic density itself, so we can simply modify this feature, which is this one, field-free embedded atom density feature, to a field-induced one, just by introducing an atomic orbital, that's a virtual orbital, added to each atom center to represent the field vector. And we add them together to the intrinsic orbitals of other neighbors, and then we can add them together and use this energy and its the gradient with respect to the field vector to reproduce the dipole and polarizability and even hyperpolarizability if you want. And we can learn them all together. And this slide just shows how it works for a toy system, the water molecule rotating in an electric field. If the field is perpendicular to the molecular plane, and when the molecule is rotating around the x-axis, then the potential energy should not change, right? And if it rotates around the y-axis, then the potential should be changed as a function of cosine theta. And also, our model captures the high-order perturbation of the system. If you use only the first order, like the dipole, permanent dipole interacting with the field, and you get a flat potential with respect to the increase of the field intensity, but our model can calculate, can capture this variance of the field. Another test system in gas phase is for the NMM molecule. We can learn energies, forces, dipoles, and polarizability together to get a very decent model. And this model can allow us to simulate the IR spectrum and Raman spectrum. And you can see here our results agree very well with the experiment when considering quantum nuclear quantum effects using the RPMD approach. And what's more interesting is that when we add an applied electric field, you can see the change of the spectrum. This is the IR spectrum, and this range corresponds to the CO stretching. And when we have an external field, the 2 peaks disappear and become only one. And that's actually a field-induced hindered rotation, because you have field right now, and the molecule has a dipole, so this CO bond is more rigid, and the CO branching disappears. And also the CO bond is softened by this external field, so its frequency is decreasing to the red end. But this application to periodical systems become more complicated. It's less straightforward, because many of you may know this multi-valued issue of polarization defined in the periodical systems. Because of the periodicity of the wave function, you can have multi-branchings of polarization. But when you do electronic structure calculations, you cannot control them. Even though many softwares can, when you do AIMD simulations, many softwares can adjust this kind of polarization to match the last step. but you can still find many, sudden jumps that correspond to the change of the polarization into different branches. But so how to capture this? If you directly learn this dipole moment for periodical systems, you will get very bad representation and high errors. But we can learn the field-independent forces in our model and retrieve the dipole moment by the definition. That's an indirect way. But in this way, we can calculate very accurate spectroscopy. And if you go the brute force way, you will get totally wrong spectrum here. And again, we can analyze how the spectrum changes with the intensity of the field, and these are just how the field interacting with the liquid water, and again the hinder rotation will increase the libration frequency, and also the alignment of the water molecule will make the whole structure more ice-like, and then the OS stretching frequency will decrease. Okay, so I guess I will skip these take-home messages because all the information I have talked about today is about how to, establish this neural network from a physically inspired way. And we also have this open source package for everybody to use, and we have some users around the world. And if you are interested, you can just go to download it. And with this, I would like to thank my whole group, actually, especially those major developers of this program, and my collaborators. Reinhard here is in the audience, and my funding agencies. And thank you all for your attention.
Now it works. So thank you, Bin, for a very interesting presentation.
Yeah, so a very clear talk. So I have two questions. So one is, so have you actually benchmarked this FIREANN regarding the prediction of polarizability, for example, using the QM7B datasets? So how does it compare, for example, this alpha ML model?
I'm not sure if I understand your question. You mean this one to predict the polarizability?
Right, because for example, this FIML model, right, generates from this group. So using a large number of organic molecules. So
I see. Yeah.
So have you tried to see what kind of performance would be given?
Yes, we did. I didn't show the results here, but in our first version of learning the polarizabilities, we already compared the performance of our model with theirs. I think the performance is similar. But for this one, this is just I think their model cannot do the polarizability with an applied field. So this is the correlation plot for all the polarizabilities, all elements of the polarizability tensor with an finite field from 0 to 0.5 V angstrom. So that's a validation for our model. We can describe not only field-free polarizability, but also field-dependent polarizabilities. Well, we did do the comparison. I can show you some results after the talk.
Right, and then just the second question is that for the periodic system, the liquid water.
Yeah.
So yes, since you can apply the field, so have you computed, for example, a direct constant of liquid water with the field applied? Yeah,
that's a good question. We haven't done that. Actually, this issue came across when we did this project. I didn't realize this before. So I would argue that many current machine learning models for learning dipoles, which work well for molecular systems, will face the same problem here. If you directly apply those models to calculate the dielectric constant, you have to be careful. Yeah. But for water, you can actually bypass this problem because water is quite a well-defined system. You can define the so-called one-year centers. So you can, indirectly learn the one-year centers, and then you can reconstruct the dipole moments. That also solves the problem. But our approach is more general.
Yeah, thanks.
Thank you.
So, Alexander?
Great talk.
Yeah.
Very cool results about polarization.
Thank you.
Can I ask a controversial question? So energy is invariant. Do you really need equivariance? Because you pay the price that your equivariant neural network probably like 20 times slower. But for invariant properties like energy, do you really need equivariance? I understand for polarization, right? It's a perfect match, but for energy and forces.
You mean for energy and forces, you don't have to use equivariant?
Yeah.
I think that's just the representation way. People call this equivariant neural network, but it's just a different type of message passing. You not only transfer or pass your scatter information, but you also pass the vectoral or tensorial information to the end, and it's independent of your output. It can be a scatter value, because when after you pass your message, you see the summation. You still sum all the information in the feature. Then the feature passed to the neural network to generate the output. So I don't think that destroys the symmetry, intrinsic symmetry of the quantity.
We have time for a final question here.
Just a question. So very nice work. A question on the FIREANN, FIREANN.
FIREANN, yeah.
FIREANN. So this is, you use the equivariant version of FIREANN to build this, or invariant?
No, in this published paper, we haven't used.
You haven't used the equivariant
yeah.
features. So a few years ago, there was a paper by Michael Gastegger where they did what they called it field-induced, which basically was the Schneid message passing with this additional input that describes the field bias. And then, so they only had scalar charge features from which they constructed dipole moments polarizabilities. Have you compared to some of their results?
You mean FaceNet?
The field-induced, yeah.
Field-induced.
Have you seen this?
Yeah,
it might be interesting to compare, because in their case, they didn't explicitly construct through the response to polarizability.
Oh, you mean field-induced, right?
That's right, yes.
Because, there are too many names in this field, so I have to recognize what you are saying. Yes, actually, this diagram in our published paper, this blue line corresponds to their model.
Oh, okay.
But I didn't show it here because,
Yeah.
but that's their problem. They only consider the first, order perturbation of this field system interaction. So only this intrinsic dipole.
So if you were now to also propagate the equivariant features through FIREANN, do you think that would make a difference, would improve things for the polarizability?
I would expect that only improve the accuracy, but I don't know how much it will improve.
So more data efficient, basically.
Yeah.
All right, cool. Thanks.
Thanks.
So with this, I think we should thank Bin and all the speakers for this session. Before